All right. Chapter 16 has to do with equilibrium and reaction rates. So the first thing in our chapter handout is we're going to be talking about the rates of a chemical reaction. So we have a definition of collision theory. So collision theory, in collision theory, our molecules are randomly colliding, and if a collision is successful, molecules will go through a transition state in which the bonds are rearranged and products are formed. So we're breaking and making bonds if we have an adequate collision in order for a reaction to occur. So basically, our molecules are colliding with other molecules, and if everything is just right, a reaction is going to occur. So we have three factors that are going to affect the rate of a reaction. So collision frequency, how often our molecules are colliding, the energy that our molecules are colliding with, and the orientation. So there are certain groups in our molecules that can react with other things. We just have to make sure that those groups are the ones that are colliding and touching in order for a reaction to occur. All right, so in order to speed up a reaction, talking about those three things, frequency, energy, and orientation. If we want to speed up the rate of a reaction, so how quickly a reaction occurs, we need to increase the frequencies of collisions, so how often they happen, the energy of the molecules. This can be our kinetic energy, so if we heat up a reaction, typically, depending on if it's exothermic or endothermic, that'll give us our molecules some energy. And then we want the right orientation. So those groups in the molecules that are going to be reacting have to touch during that. So in these pictures here, we have a reaction with a fast rate, and on the right we have a reaction with a slow rate. So basically, as time goes on, our reaction here occurs really quickly. Notice how we only have products by the time we get to the third and fourth frame. But here with the slow reaction rate, we still have reactants and products by these times. So these guys are colliding really quickly, and if they have the right energy and orientation, we get our products. But these guys, they have less frequency probably, maybe less energy, or the orientation isn't right. So we still have reactants after the same amount of time has passed. All right. So there are three factors that affect the speed at which a chemical reaction proceeds. So we're going to be looking at the reaction concentration. So if we have a low initial concentration of our reactants, we're going to have a slow rate, a slow initial rate. But if we have a high concentration of our reactants, we're going to have a fast rate. We have a lot more molecules that can perform in the reaction to make us products. The effect of temperature on reaction rate: if we have a low temperature, our molecules are going to move slower, so they have less kinetic energy, so movement of motion, kinetic energy, and they're just not going to collide as often, and with not enough energy. So we're going to have a slow rate if we have a low temperature. If we increase the temperature, our molecules are moving a lot faster, and we get a fast reaction rate. That's to an extent. There is a cap on the temperature, because if our molecules are moving too fast and they just zoom past each other, a reaction's not going to occur. So we can increase the temperature to an extent in order to get a fast reaction rate. And then 3, the presence of a catalyst. So a catalyst, we've talked about this before, but a catalyst speeds up a reaction by increasing the number of effective collisions. So basically, an enzyme in your body is a catalyst, so it grabs your reactants and it orients them in the right way in order to make our products. So that's basically what a catalyst is doing. So it speeds up our reaction that way. All right, so student exercises. Okay, give one reason insects move more slowly in the fall of the year, and explain. So basically, we have a decrease in temperature in the fall, which is going to cause a decrease in reaction rates. And insects are cold-blooded, so environmental temperatures are going to affect the bodily reactions of our insects because they're cold-blooded. They can't make their own heat, and thus their reaction rates are dependent on temperature. All right. Use temperature effects to explain how hibernating animals can go for long periods of time without food. So same thing, temperature. So if we have a decrease in temperature, we're going to slow down the reactions in our body, including the biochemical reactions in the body. So decrease in temperature slows down reactions, including biochemical reactions in the body. All right, if all other factors are kept constant, what effect would decreasing the concentration of reactants have on the rate of the reaction? So if we decrease the reaction rate, we're going to have less collisions. So if we have, it decreases the reaction rate and we have less collisions. So if we have less reactants, we're going to have less collisions and thus decrease the reaction rate. All right, according to collision theory, which of the following factors influences the rate of a chemical reaction? So we got 3 things. So frequency of molecular collisions, that was on the previous page. Energy of molecular collisions, also on the previous page, and orientation of our collision. So all 3 of those are going to affect the rate of a chemical reaction. All right, next we're looking at energy profiles of chemical reactions. So we have, we got a bunch of definitions here. Let's look at the definitions first before we look at any diagrams. So our activation energy. So in this diagram down here, the activation energy is labeled. So the activation energy is the energy that must be supplied in order to get a reaction started. So these reactions, we do need some energy in order for them to react. And that's our activation energy. So the energy of our reactants up to the part of our highest point in our graph. So that's our activation energy. We require some amount of energy, even if it's small, even in exothermic reactions, especially in exothermic reactions. We just gotta like give them a little push, like, hey, you guys should react. And once we've gotten over that threshold, everything else, the molecules do everything else on their own. Next definition, catalyst. So a catalyst is going to lower the activation energy and increases the rate of a chemical reaction. So that's what this drawing is up here. I highlighted the parts of the reactant energy diagram, in pink. So with a catalyst, without a catalyst, though we need a certain amount of energy to get to that threshold. But without a catalyst, with a catalyst, the catalyst is going to make up that difference in energy. And so the energy that's required to start that reaction is a lot less. So without a catalyst, we got to get to that activation energy, the normal activation energy, but with a catalyst, that catalyst lowers the activation energy by a lot. All right, enzymes, biological catalysts, like I talked about 30 seconds ago. A reaction profile. So that shows the energy of reactants and products during the course of reaction. So this is a reaction profile, also known as a potential energy diagram. Okay, transition state. So the highest point in the reaction profile. So that is this guy right here. I labeled it in pink. So the highest point of the reaction profile. So at this point, bonds are breaking and simultaneously other bonds are forming. So bonds are breaking and forming at the same time in this transition state. So we're going from reactants to products. Breaking bonds, forming new bonds. The heat of the reaction is the energy difference between reactants and products. So our energy of reactants is here, energy of products is here. So our heat of reaction is this guy right here. So that is our heat of reaction, delta H reaction. Okay, exothermic reaction, we know this, it proceeds by releasing heat energy. So here, this is exothermic. Our energy of our reactants is higher than the energy of products, so we are releasing energy to get to there. Both of these are exothermic. The next student exercise is a endothermic reaction. But endothermic absorbs heat and proceeds by consuming heat energy. So we need to put in heat energy in order for that reaction to occur. So let's look at, here we go, the student exercise. So student exercise not labeled. Ultraviolet light from the sun converts oxygen molecules in the upper atmosphere to ozone molecules. So ozone is O3. Draw the reaction profile for the endothermic reaction. So we are putting in heat energy in order for us to convert oxygen to ozone. So in our energy diagram, we have energy on the left, on our y-axis, and then we have the reaction proceeding on the x-axis. So if we are endothermic, our reactants are going to be less, with a lower energy than our products are. So we're going to draw our reactants lower and our products higher. So we have to put in a certain amount of energy. So our activation energy is up until this transition state here. So that big dot that I just drew, that's our transition state. We got to put in heat energy until we get there. But our products, their energy is going to be slightly less than the activation energy. So that part right there is just a little exothermic. But for overall, we are definitely an endothermic reaction. We have to put in all of this energy to get to the activation energy, and then our reactants are going to do, they're going to combine and form our products. So at this point, you can do the potential energy diagram worksheet. So use the definitions on page 2 of your chapter handout and these pictures here to help you answer that worksheet.